Okay, I'd like to finish up 4.3, talking about this this statement right here. Now, from our definitions earlier, and I will prove this in two ways, like the book is going to do, and I'll show you how. I'll take a slightly different approach in the way I prove it using the things from the chart. So, what I would like to do first is show you the element proof. Now, if you remember from the previous video, when I say that two sets are equal, and it may seem a little bit weird, but this is a set, right? This is some other set, right? I could call this set C and D, right? So if I want to show sets C and D are equal, well, notice that I have to show that, so I have to show that both C is a subset of D and that D is a subset of C. Right. And to do this, right, remember when we were showing things are subsets of one another, if I want to show that C is a subset of D, if I start with an arbitrary element in this set I'm calling C, which is the union of A and B, I want to show that that element is also an element in this other set, A union A complement intersect B. Right? Now to do this, what we'll need to do is we'll need to think about sort of logical ways we can do this, right? So let's start out by first suppose X is an arbitrary element, right? So suppose X is in A union B. Right, so let's suppose, and I'll put parentheses around this to make it explicit that it's an element of both in this case. So for X to be in there, I know by definition, right, by definition, and notice this is really similar to the way we were writing proofs in chapter 3, right? We suppose that something is, it has some arbitrary property, and we use the definition of that property. Now notice that what we were doing there really is talking about sets, right? But we didn't say we were talking about sets, right? We said we were talking about like integers, or even integers, or odd integers, or divisible by something, right? Notice that we can think of those in a real abstract way as all being part of talking about sets, right? There's a set of odd integers, right? If something belongs to that set, right, by definition of what it means to belong to that set, I know something about that element. So here, for it to belong to this set A union B, I know that X is in A, or, right, X is in B. Now, something that's kind of not obvious that we're going to do here, and I don't know, I'll say the more we do this, I guess the more it'll make sense. But one thing we could say is that by virtue of being an element in, let's say, the universe, we can also say that X is in A, right? Or X is in A complement. Now, the reason I know to do this is because I need to introduce an A complement somehow, and this is about as good as it can get, right? So let me think if I can put these both together, right? Then I think what we're going to do is we're going to see how it all comes out, right? Now notice I can write something like this. I can write X is in A, or, right, X is in A complement. I could also say something like and right? Because X is an element of this set, right? It's a universal set, so this is kind of a weird thing, but it's true. So it's there, and I know it's in A or B. So X is in A. Or, right? X is in B. So notice that I can pull this and this out. Right? And what I'm going to be left with right, I guess I should be writing equivalences every time here. So really, I'm saying that this is equivalent to X being in A or B, and I know that the other thing was an equivalent statement for being in A. So X is in A, or, right, because the distributive law is what we're going to use here. X in, we'll say A complement, and, right, X is in B. By sort of these definitions that we were working with before, right, I'll say that this is equivalent to the previous statement. If X is in A, or X is in A complement intersect, and X in B complement, just X and B, can't say words. Notice that I can sort of take this to the, let's say, the larger world and show that, right, X is in A union, right, A complement intersect B. So what I did is I started with A being an element of A union B, and what I wound up with is, X is an element of A union B, and I wound up with X being an element of A union A complement intersect B. So now I want to show, I've shown that A union B is a subset of A union A complement intersect B. So now I want to go the other way, right? Now I want to show that, well, I'm going to use my C and D as before. Now I want to show, well, no, I guess I don't want to show. I won't use C and D. I want to show that A complement, I'm sorry, that's not right. A union A complement intersect B. I want to show that that's a subset of A union B. And if I show that that's a subset of A union B, then by showing that they're both subsets of each other, I've shown that that they're equal. The sets are equal because, you know, if something contains at least the same elements as one, the other, then I know that they have to contain the exact same elements. So first I'm going to start out by supposing. So suppose X is an arbitrary element of this set. So what do I know? Well, let me break this apart and say that this tells me, right, by definition, that X is in A, or, right, I know X is in A complement, sort of going by the definition. I guess if I went like step by step, I could have said that X is in A or X is in this other thing, A complement intersect B, and then I could have pulled it out more, but I'll just go straight to this. Now notice when we have it this way, something I could do here instead of saying that X is in A complement, I could say that X is not in A. Right? That's another kind of way we can think about the complement. And if we do some distribution here, I'll have something like X is in A, or I could say X is in A complement or not in A. I'll just do A complement. Notice that this is basically going to get us pulled back to where we were at the very beginning. And then I've got this and, right, X in A, right, or X is in B. Notice another way I can think about this. If X is an element of A or not A, I think the book refers to this as a tautology in logic. I mean, I guess I'll buy that, sure. We could think of this as a tautological, an instance of a tautology or tautological statement. If we're thinking about sets, another way to think about this is just that this is the universal set. So if it's in A or not in A, that just means that X is in the universal set. But we can think of this as a tautology. Sure. I'll do it that way. So tautology and, right, And remember that if we have any logical statement with a tautology, right, with this conjunction, the and, right, that tautology and something is just that thing itself, right? Basically, you're intersecting this with that. And so the tautology and the set, right, is just the set. So notice that that's going to give me just, I've been bad about writing equivalent to here. Notice that's going to give me this equivalent statement that x is in A, or, right, x is in B. And what do I know by definition is that this means that x is an element of A union B. Right. So I've shown both ways, right? Well, I've shown both ways to get it to show that the set is equal. Now, I'm going to use a different method, right? So this was an element method by supposing x is an element in our sets and showing that the sets are subsets of one another. So let's look at one more way to do it. And this is just using some definitions from the table. Now, I'm actually going to do it a slightly different way. I want to show that this is true, that A union B is equal to A union, right, A complement intersect B. I'm going to do this slightly different than the way the book does it. The book starts here, and then they get to here. But I'm going to go the other way because I think it's easier, and to be honest with you, it doesn't matter because I'm showing the sets are equal. So as long as I'm using equivalent statements, I should get to the same thing. So note that if I start here, A union A complement intersect B, and I'm going to use distributive, right? I'm going to distribute the union over the intersection, just like we do the or over the and. Notice here I'll get A union A intersect. I'm sorry, A complement intersect, right? A union B. Right. So this is equivalent statement. Another equivalent thing I can do. This is just a universal set. So I've got the universe. I can't write it as nicely, but the universe intersect A union B. And notice that the universal set is in fact an identity element for the intersection operation. So, huzzah. As we wanted to show, that's true. Now, something I'll say is that sometimes one method is not necessarily obvious. And so you might want to try one method over another. So both of these actually proved that they're equivalent. Now sometimes an equivalence might not exist that's on that sheet, and so maybe you have to prove it using the element methods. All right, that's it for now.